Okay, so now we're ready to carry on with more reviewing. We don't have too much further to go with that. After this session and maybe a little bit more of the next one, we'll be ready for the new material. But right now, we're going to dive into an extremely important concept, which is essentially the reverse of differentiation, and it's called integration. Okay, so in other words, we're going to take, instead of taking the derivative of a function, we're going to reverse engineer that. We're going to take the derivative and work it back to the original function. So we're going to start by introducing the concept of antiderivatives. Okay. Now, you may have heard the prefix anti just means that we do the reverse. In fact, in some countries, you may have noticed that while we here discuss the directions clockwise and counterclockwise, in some countries, the direction we call counterclockwise is referred to as anti-clockwise because it's just the reverse of clockwise. So the same thing is true here. Anti simply means we're reversing whatever we did to take a derivative. We're working that backwards to take an antiderivative. Now, I have to tell you right up front, taking antiderivatives, in my opinion, is much more difficult and complicated than derivatives. In fact, if you want to know how much more complicated it is, if you look at the back of the book at all the different tables that are back there, the list of um, rules for derivatives is quite small compared to the table of antiderivatives, which is quite massive. It spills over several different pages, and that's just an indication of how complicated this process really is. So here we're going to introduce some basic notation. So imagine we have a function f of x equals 3x squared. Very simple. And we know that the derivative of x cubed using the power rule is 3x squared. So what this means then is that the antiderivative, as it's called, and by the way, we're going to designate that with a capital F, um, is x cubed. All right. So in other words, f of x is 3x squared, lowercase f. Capital F of x is x cubed. Oh, okay. So I've got to be careful here to make sure that lowercase f's are distinguishable from the uppercase f's. So if our original function is f of x equals 3x squared, the antiderivative of 3x squared is x cubed because the derivative of 3x of x cubed brings us back to our original function, f of x. Okay, so in a nutshell, this is what we're going to be doing. We're going to go from whatever this function is, and we're going to say what function has a derivative of 3x squared. That's what we're trying to do. Now, of course, what we don't see here is how did we figure this out? How do we know, for example, that the antiderivative of 3x squared is in fact 3x cubed, or x cubed rather? So that's what we're going to work on now. Let's see, they got a few more here. Now, oh, by the way, this is one of the peculiar things though about antiderivatives. Um, it turns out that we know that the derivative of x cubed is 3x squared. Fine. But guess what? The same thing could be said for x cubed plus 1. Ooh. And x cubed plus 2. In fact, for any constant, we're going to get the same result. So what that means then is that the antiderivative is not unique. There can, in principle, be any number of functions that represent our antiderivative, but all of them are only different by a constant. Okay, so in other words, whichever one it happens to be, um, whoops, what did I do here? Is going to be the same. It's going to be x cubed, 3x squared rather, with a constant attached to it. Okay. So we could think of, in general terms, f of x can be written as, instead of just x cubed, we're going to write it as x cubed plus c, where c could be anything, including 0. And that's because the derivative of this antiderivative will give us back the original function of 3x squared. So this is something we have to get into the habit of remembering. Every time we apply this process, we're going to have to remember to supply a constant, because we know that the constant itself is something we can't figure out with other information. But in general, we'll just write it like this. Okay. So, so f is an antiderivative when f prime of x. So you notice what they're doing here. Instead of calling it d, like I have d f of x, we could also call this capital F prime of x. It means the same thing. All right. And of course, they're just messing around with the notation, but the c is called the constant of integration, because the process of taking an antiderivative is actually known as integration. All right, let me just get this straight here. And yes, taking an antiderivative is referred to as integration. All right. What are we doing here? Solving a differential equation. So imagine we have the following equation, dy dx equals 2. This is known as a differential equation because it contains a derivative. I mean, it's really that simple. And by the way, if you're a math major, you may look ahead into the catalog to see where you're headed in your major. Most schools do offer an entire semester of differential equations if for the math majors. And if you are a math major, you might want to consider taking this course because it really is extremely helpful. It really covers a lot of important ground, and it might look terrifying when you look in the book and see what's going on in there, but it really is very straightforward and down to earth. So just a little side note there. This is an important branch of mathematics. But anyway, so what they want you to do is you're saying, um, keep in mind, this is the same thing as f prime of x. So what we're trying to do is find f of x. Okay. Now, they're not going to tell us how to actually do this, but they are going to tell us that 2x works. Okay. So in other words, if y equals 2x, dy dx equals 2. Okay. So therefore, this means that, and we'll add the c here, is the antiderivative of f of x equals 2x. Sorry, of equals 2. There we go. Okay. Now here they're just showing us that by writing it in this form, and they're writing it as y. I mean, we can easily, just as easily write this as y equals 2x plus c. They want you to see that all the potential antiderivatives are just different by constant, which means they're parallel to each other. Now, if we had more information, we could identify which one is the correct antiderivative, but without that information, we'll just leave it as 2x plus c. All right, let's see. Sometimes you see these different, but by the way, just as a quick reminder, as far as the notation is concerned, we call that a differential. It is, think of it as an infinite or infinitely small change in y. And you can think of now, you've encountered many times before this notion of delta y, which is a small change in y, which we use, of course, to help calculate a slope, delta y over delta x. But when the change is infinitesimally small, we call it now a differential, and we write it as dy instead of delta y. So what we'll see sometimes here is that since dy dx is the same thing as f. Oh, okay. No, I see what they're doing is they're setting it up as a differential equation. So they just want you to see that you can write it like this if there's a good reason for it. And this is a differential equation. All right. So they're going to write this in the most general possible. Now, this is the first time we're going to see this symbol, by the way. So this is the integral symbol. It looks like a big S. And as it turns out, this represents an infinite sum. And in fact, some people think that the reason why we have this S symbol is because if you take your summation symbol and sort of stretch it out, it becomes an S. It's hard to say sometimes where these symbols come from. Somewhere along the way, some mathematician decided that it looked like the way to go, and that's what we've had ever since. But so this represents a sum. This is an integral, which is an infinite sum. So when you see that symbol, it means we're finding the antiderivative of that function. Okay. Now, oh, also, by the way, I just want to point out that, so in other words, what they've actually done here is they've just simply applied the symbol to both sides of this equation here and here, and this is the result. Now we can learn some rules. So, and again, we have so many different potential symbols. Um, Keep in mind that f prime, okay. Oh, actually, I guess this is the first time we've seen f prime. Okay, so keep in mind these both mean the same thing. Whoops, no, they don't. Sorry. What did I do? Okay. So basically, all they're telling you here is that integrating and differentiating are inverses of each other. In other words, they bring us back to the same function. All right, now we get to have some rules. All right, now if you notice, the rules on the left we've already covered. The ones on the right are the ones that correspond to the ones on the left. So it's quite an impressive long list here. So let's see what they've got for us. All right, so there's no mystery about any of these. Um, just be aware that, of course, f prime of x, in case they change the notation somewhere along the way, this is the same thing as this. But then, so those we know very well. We just went through those. But these are new. So when we integrate, as it's called, so and again, you notice how they're using the word integration. The process of finding an antiderivative is known as integration. So the integral of zero, now keep in mind, every one of these is going to end up, there's a constant at the end because we know that there's an infinite number of possible results here. So if we integrate zero, we'll just get c. K. And by the way, if you're not sure, you can just double check by taking the derivative of this result. For example, you could double check that by saying, well, is it true that this is equal to K? And the answer is yes. Okay, so that must be the correct result. Now here, this just means we can factor out the K, which because it's a constant. Now here, you can see the integral of a sum or difference is equal to the sum or difference of the integrals. And here we have a power rule where, since we're going in reverse from what we're used to seeing, you'll have x to the n plus 1 over n plus 1 plus c, but we may not let n equals negative 1. If it does, we have a different rule for that. Okay, so in other words, not 3, x to the third power. Well, clearly n is 3. Okay, and again, you can easily check this. So the derivative of c, of course, is just 0. We don't have to worry about that. I've factored out the 1/4 from this expression, and now we're going to use the power rule for differentiation. Um, let's see. Whoops. Hold on. So we'll have, just as I just threw that in there as a quick reminder. And so that, I mean, that means we did it correctly. We start out with x cubed under the integral sign, and that led us to x to the fourth over 4 plus c. When we differentiate x to the fourth over 4 plus c, it brings us back to x cubed. Okay, good. And that's it for now. Now, of course, we have to deal with trig functions as well. And so you can see, um, in a lot of ways, they're just simply reversing the process. So, for example, if the derivative of sine x is the cosine, the integral of the cosine must be the sine. If the derivative of cosine of x is negative sine x, the integral of positive sine x must be negative cosine x. And you work your way down, you'll see the correspondences between them. All right, so here's a simple one. Um, Integral 3x dx. So remember the way this works. And since here, um, n is 1, there's an implicit 1 here. Okay, so you're going to end up with, and by the way, since this c is just a constant, you don't have to bother multiplying it by 3. You can leave it as c. It's understood that this is a constant whose value we don't know. So therefore, you can just leave it like that. Right. So yes, if you were given more information, you could figure out the C, but we're not going to do that just yet. Whoa, look at this one. All right. Sometimes what they're trying to help us see here is that sometimes it's easier to split it up into pieces. You know, the thing about integration is because it's such a messy process, there's often going to be a lot of strategies dedicated towards simplifying our integrals to make it easier to get them done. Because again, these are going to be very complicated compared with derivatives. So here, what they're saying is, well, we don't think we don't seem to have a rule for this one, so what can we do? And why are we doing this? Because you can see that in the first case, okay, so remember the quotient rule for exponents. If you have x to the a power over x to the b power, that is the same thing as x to the a minus b. So that means this first expression is just radical x. In the second case, 1 over radical x means x to the minus 1/2 power. So we can rewrite this whole thing as um, actually, I think we should probably leave it like this. And now we can apply the power rule. Okay. So again, this is how it works for integrals. Don't forget the C. So that means the first one is x to the 3/2 over 3/2. The second one is x to the 1/2 over 1/2. And again, you've got these two unknown constants. You can just lump them together because we don't know what they are anyway. Also, you might want to simplify it a little. This first term could be rewritten as 2/3 x to the 3/2. This one could be written as 2x to the 1/2. And then we have a constant. All right. And we're done. Okay. Now, if you do really need to know the constant, that's what this is all about. Initial conditions and particular solutions. So here they're giving us this wonderful little graph to show that this particular integral gives us x cubed minus x plus c. So these are all the curves that potentially can give us the solution, and they're all different by a constant. Okay. But what if we do need to know the actual value of C? We have to be given what's called an initial condition. And so, like here, just as a quick, simple example, if you're told that the antiderivative is x cubed minus x plus c, but we're also told that our solution cuts to the point 2, 4, then we can substitute here. Um, and so we're told that um, when x equals 2, y equals 4. So what do we do then? Well, f of 2, let's write this down. F of x is x cubed minus x plus c, but we're also being told that f of 2 equals 4. On the other hand, f of 2 equals 2 cubed minus 2 plus c. So we know that f of 2 is 4. We also know that it's 6 plus c. So of course we set these equal to each other. The constant is -2, and therefore our solution is x cubed minus x minus 2. This is the antiderivative that we're looking for. All right. Oh, okay. No, it's just another example. Okay. F of x is 1 over x squared. Now, of course, we disallow for x to be equal to 0. The initial condition, as it's called, f of 1 equals 0. Okay. Now, of course, for to put it into the right form, let's do this. Let's rewrite this as x to the minus 2 and recall the rule, power rule. And that'll give us, and then we can rewrite this. It's a little messy. We'll rewrite it as -1 over x plus c. But we also know that f of 1 equals 0. So, therefore, since we started out with f of x equals 1 over x squared, Um, and f of x is negative 1 over x plus c. So we ultimately end up with, okay. And that identifies which of these curves is the right one. Oh, you know what I just noticed? I missed the prime here. No wonder it was so tiny. All right, that's better. Oh, sorry. That means this is not correct. This should be capital F. Yeah, I just realized there was a prime there that I overlooked. Sorry. Okay, now we're good. All right. So here's one. They just want us to do a quick check to make sure we can understand. Now, by the way, if you notice, they keep referring to this as an indefinite integral to distinguish it from a definite integral, which we'll get to in the next section. Um, so we have the integral of, all right, we have this integral. So we're basically going to break it up into three parts. Okay. Now we can factor out the constants. And then we can apply the power rule. And so what do we end up with? Don't forget the C. Um, and then in a second, we'll simplify them. And again, because each one of these has its own constant, but then we can just lump them together. So we don't have to worry about that. So we end up ultimately with minus 3t cubed plus 7t squared minus 2t plus c. Okay. And so which one is that? It looks like the answer is D, C rather. It's C. Very good. All right, so we don't have to do every single one of these. Let's move on to 4.2 and area. So what they're basically, yeah, they're giving us some more background here, but keep in mind where's this going? I just want to remind you from your travels that if we have some function or other, the area under this curve between these two endpoints is actually the integral of f of x specifically evaluated between a and b. And when you evaluate it with specific constants like that, it becomes a definite integral. And that means we don't need the plus c part. So the reason why they're all of a sudden talking about area is because they're building up to this idea that the area under the curve is nothing but the integral of the function between those 2 points. So it's important that we understand what area means, okay? All right, here we go. So we have terms, some kind of sequence, And if we want to write a sum, we already know this sigma notation. Here, it's a finite sum. Okay. Now they could make it is possible for this to be an infinite sum. We're not doing that here. Um, Now, I don't know what happened here. See, this is one of the peculiar things about switching back and forth between Macs and PCs. I've seen this before. Sometimes when there's special symbols, it doesn't show up correctly on one of the platforms. And so you can see here, this L here is clearly not what they meant. Um, oh, here it is. This was supposed to be the ellipsis. Okay. Like what I have here. So somehow it got misinterpreted on the PowerPoint slide as an L. So you have to keep an eye on that. Symbols every so often get misinterpreted because you might be looking at it on a Mac when it was created on a PC or whatever the case may be. I is the index of summation. And yes, if you weren't sure, these three dots are called an ellipsis. Okay, they're used in math, of course, to indicate that something is missing, but the pattern should be clear. It's also used in English too, in paragraphs where they're leaving out parts of it from a quote, let's say. So anyway, so I is the index of summation. Um, AI is referred to as the ith term. Okay. And the bounds are 1 and n. Yeah, so this is pretty normal for summation notation. And yeah, here they're showing you some examples. You're basically just plugging in. Now, you notice how in the second case it started at zero. There's nothing to prevent it from starting at zero or any number for that matter. It doesn't have to be any particular number, but usually it's either zero or one. Down here's an interesting one because you notice how they're adding up not j, but j squared. So you've got three squared. Oh, here it is. We started at three instead of one. So we got three squared, four squared, five squared, six squared, and seven squared all added up. And then, yeah, well, look at these. Oh my God. But it's the same thing. And again, there is that stupid L there. You got to keep an eye on that. As far as these go, they have their own set of algebraic properties. For example, you can see that you can factor out a constant from a sum. It won't affect the results. We have the sums and differences um, of these series that you add them up or you subtract them as the case may be. Now, here's where it gets interesting. It turns out that some of these have closed form solutions. So, for example, well, C, what does this even indicate? A sum of C's. Yeah, that's all it is. But look at these. Now, the sum of the first I terms is n plus 1 over 2. Interesting. So, in other words, let's say, for example, I'm looking at, so I'm adding up the first five terms, natural numbers. So that means it would be written like this. And I mean, n is 5. So I'm going to have 5 times 6 over 2, 15. And you can see, if you just add these up, you can see it is 15. We also have a formula for I squared. A bit messier, as you can see. God, I've got so much stuff open up, I can hardly see what I'm doing. Here it is. All right. It gets like this sometimes. I'm using this tablet. It's not exactly an expensive tablet, and it gets quirky sometimes. Okay. Now, nobody's expecting you to memorize these, but it's good to know that they exist because there'll be times when it might come in handy for reducing an expression to something much more complicated, much less complicated. All right, so that's a good point. Now, it turns out later on we'll see that there's a lot of functions that we know can also be expressed as sums of terms like this. In some cases, infinite sums. But it's quite interesting what can be done with these formulas. So yeah, I guess we don't have to go through every single one of these, but now they're kind of finally building up to this notion of what we're trying to do with integrals. Okay, so we don't, you can read this part if you want to remember, the area of a triangle and all the rest of these. But here is what we're really after. This is really where they're getting into the meat and potatoes of this. What exactly are we doing when we integrate? That's what we're trying to find out right here. So we have the same function. They're showing this to us in two equivalent ways. Now, clearly, this is a parabola facing downward. What we're trying to do is estimate the area under the curve, and we're doing it by creating a series of rectangles. If we do this well, the area of the rectangle should be at least a good approximation to the actual area under the curve. Now, there's two equivalent ways of doing this. Each rectangle has, of course, a left endpoint and a right endpoint. So let's say this is the real number line. Here's a rectangle. The rectangle has to have a flat top. Um, Otherwise, it's not a rectangle. And so what we're going to do here is on the left, we have rectangles drawn so that once we choose the left endpoint, we then connect the top of the rectangle to the next, um, to the curve. Okay. Or in other words, each of these has to have the same width, which as you can see in this case is 2/5. So once we've chosen the left endpoint, we move over to a right endpoint, and then we draw our rectangle. Okay. So we start with the left, move across to the next endpoint, which is the right endpoint for this one. And you can see we end up with this setup. Over here, it's the other way around. We have the right endpoint, and the idea here is that the left endpoint is touching the curve in each case. Whereas over here, we made sure that it's the right endpoint that always touches the curve. Okay, so what's different between the two graphs is whether we're letting the curve, the rectangles touch the curve at the right endpoint or the left endpoint. And of course, with the curve the way it is, the one on the left, as you can see, the rectangles are understating the area under the curve. If the curve had a different shape, that might not be the case, but here the rectangles understate the total area under the curve. On the right, it's the other way around. Now, what can we do about this? Well, one thing we can try is to reduce the widths of these rectangles. If we had a larger number of more narrow rectangles, the approximation would continue to improve. And in the limit, the two would give us the exact same result, which in turn would match up the area under the curve. Okay, so that's where we're heading with this. As the number of rectangles increases, the approximation improves, and both approaches will converge to the actual area under the curve. Okay, so if we have an infinite number of rectangles, of course, we need to solve for an infinite sum, and that's where the integral comes in. Okay, that's where this is going. We need an infinite sum to get the correct answer, and therefore we're going to use integration. So now you know the cat is out of the bag. Where is this headed? All right. So yeah, they're giving us a rough idea. They're showing us what the actual areas are. The one on the left, the ones that are understating are 648. The ones on the right are 808. And of course, the actual area is in between somewhere. All right. So what we're going to do is break up this area. Now, with the integration, we're going to try to find the actual area under the curve. Um, so we're going to break up the area into intervals or subintervals, and the width, we choose the width. That'll depend or determine the number of rectangles. So we have some upper and lower limits, A and B. The difference between them divided by the number of rectangles that we use will define the width of these rectangles. And we have the endpoints. A is the left endpoint, remember, the entire interval. We start at A, and then each delta x is the next rectangle. So those are our endpoints, which we're calling 0. I don't know if you know, I guess they didn't use that notation here. Instead of having actual constants, You could write the endpoints as, all right, well, this isn't perfect, but you get the idea. Okay, so those are the endpoints. Oh, by the way, I forgot to mention this. As far as the English is concerned, and I don't know where these terms came from, but the setup we have on the left, here we say that the rectangles, we could look this up, I guess, in the dictionary. Here we say the rectangles are inscribed, as they're called. And over here, in other words, over here where the left endpoints are touching the curve, the rectangles are circumscribed. I'm sure these come from Greek. I don't speak Greek, so I don't know enough about it, but I'm sure if we looked it up, we'll discover that these are based on Greek words because the Greeks, of course, invented geometry. And so we have rectangles are inscribed and the rectangles on the right are circumscribed. And of course, the true area is somewhere in between, but as we keep shrinking up the width of those rectangles in the limit, we'll have the same area in both approaches, which in turn is the area under the curve. Now they're also going to refer to the sum of the rectangles on the left as the lower sum and on the right as the upper sum. And so you can see where they're going with this. The lower sum, Sn, is here. If we added up all these rectangles, and this, of course, must be the upper sum, and this is the actual area. Okay, so what they're going to do is run through here. Wow, this looks like a complicated example. Where we're basically going to try to represent the area correctly, but um, yeah, I don't want to rush through this part. It's awfully important. So I'll tell you what, why don't we stop right here? And the next time we'll pick it up with this example. And then in 4.3, um, we're going to introduce the concept of Riemann sums. So we're slowly building up to the definition of integration. And, we don't have to go berserk with all the theory, but we do want to remind ourselves how all this works. And then when we're done, we'll go through the rules of integration and then we'll be all set for the new material. Woohoo. Okay. All right. So we'll stop here. And then when we get back, we'll pick it up with this discussion in 4.3 we're still in. And um sorry, 4.2. We're still in 4.2. Then next time we'll start 4.3. So we'll leave it right here and I'll see you next time. Okay.